Welcome to the InnoGuide podcast, where we share the works of authors and mentors to guide innovation. In podcast 6, I am sharing part 1 of Artificial Intelligence, A Guide for Thinking Humans by Melanie Mitchell. This book arose from my attempt to understand the true state of affairs in artificial intelligence, what computers can do now, and what we can expect from them over the next decades. In the chapters that follow, I try to sort out how far artificial intelligence has come, as well as elucidate its disparate and sometimes conflicting goals, investigating how successful they are, where their limitations lie, the extent to which computers can now do things that we believe to require high levels of intelligence, beating humans at demanding games, translating languages, answering complex questions, navigating vehicles in challenging terrain. I examine how they fare at things we take for granted, the everyday tasks we humans perform without conscious thought, recognizing faces and objects in images, understanding spoken language and written text, and using the most basic common sense. What do we actually mean by general human or even superhuman intelligence? What are the dangers? What aspects of our intelligence do we most cherish? And to what extent would human-level AI challenge how we think about our own humanness? This book is an in-depth exploration of some of the AI methods that probably affect your life or will soon, as well as the AI efforts that perhaps go furthest in challenging our sense of human uniqueness. Either we are within a spitting distance of true AI, or it is centuries away. AI will solve all our problems, put us all out of a job, destroy the human race, or cheapen our humanity. It's either a noble quest or summoning the demon. This was written by Melanie Mitchell in her book entitled Artificial Intelligence, A Guide for Thinking Humans. Artificial Intelligence, A Guide for Thinking Humans was written and published in 2019. So one of the things I'll be doing, because this was 5 years ago, 2019, and there have been so many changes, so many updates to the field of artificial intelligence with OpenAI, ChatGPT, Bard, all of the other things that have come along, I'm actually going to merge in a talk that Melanie Mitchell did in March 2024. She was a speaker at UC Davis College of Engineering, where she did a presentation beginning with a brief history of artificial intelligence and then going into some of the changes that have occurred since then. So I'll be altering some of what's in the book. I will be just saying that this has now been replaced by something from the presentation, and I will note that as we go along. So without further ado, let's get going. Most people in artificial intelligence trace the field's start to a small workshop in 1956 at Dartmouth College, organized by a young mathematician named John McCarthy. He was 28. He was in the mathematics faculty at Dartmouth, and as an undergraduate, he had learned a bit about both psychology and the nascent field of automata theory, later to become computer science, and had become intrigued with the idea of creating a thinking machine. So he met another student there, Marvin Minsky, who shared his fascination with the potential for intelligent computers. After graduating, McCarthy was at Bell Labs and IBM for a short period of time, and then he met Claude Shannon and Nathaniel Rochester, a pioneering electrical engineer. McCarthy persuaded Minsky, Shannon, and Rochester to help him organize a 2-month, 10-man study of artificial intelligence to be carried out during the summer of 1956. The term artificial intelligence was McCarthy's invention. He wanted to distinguish the field from a related effort called cybernetics. He later admitted nobody really liked the name. After all, the goal was genuine, not artificial intelligence, but he had to call it something, so that's what it was called. They submitted the proposal to the Rockefeller Foundation asking for funding for this summer workshop, and it listed a set of topics to be discussed: natural language processing, neural networks, machine learning, abstract concepts, reasoning, and creativity that have continued to define the field to the present day. Think about this. This is 1956 that they're doing that. McCarthy and his colleagues were optimistic that AI was in close reach. We think that a significant advance can be made in one or more of these problems if a carefully selected group of scientists work on it together for a summer. As a result of that, McCarthy founded the Stanford AI Project with the goal of building a fully intelligent machine in a decade. Herbert Simon, one of the other members of this team, predicted machines would be capable within 20 years of doing any work that a man can do. Marvin Minsky, founder of the MIT AI Lab, forecast that within a generation, the problems of creating artificial intelligence will be substantially solved. None of these predicted events have yet to come to pass. So this was 1950s to 1960 timeframe. So we have to define our terms here. And we quote 18th century philosopher Voltaire, "Define your terms or we shall never understand one another." Marvin Minsky himself coined the phrase suitcase word for terms like intelligence and its many cousins, such as thinking, cognition, consciousness, and emotion. Each is packed like a suitcase with a jumble of different meanings. Artificial intelligence inherits this packing problem, sporting different meanings in different contexts. As for human intelligence, IQ is measured on a single scale, but then we talk about the different dimensions: verbal, spatial, logical, artistic, social. Thus, intelligence can be binary, something is or is not intelligent, or on a continuum. One thing is more intelligent than the other thing, or multidimensional. Somebody can have high verbal intelligence but low emotional intelligence. Indeed, the word intelligence is an overpacked suitcase, zipper on the verge of breaking. So, all proponents of AI simply want to create computer programs that perform tasks as well as or better than humans, without worrying about whether these programs are actually thinking the way humans think. The lack of a precise, universally accepted definition of AI probably has helped the field to grow, blossom, and advance at an ever-accelerating pace. AI is a field that includes a broad set of approaches with the goal of creating machines with intelligence. Deep learning is one such approach. Deep learning is itself one method amongst many in a field of machine learning, a subfield of AI in which machines learn from data or from their own experiences. To better understand these distinctions, let's understand the philosophical split that occurred early in the AI research community, the split between so-called symbolic and sub-symbolic AI. In symbolic AI, the program's knowledge consists of words or phrases, the symbols, typically understandable to a human, along with rules by which the program can combine and process these symbols in order to perform its assigned task. One of the early AI programs was confidently called the General Problem Solver, or GPS. Yeah, that's before Global Positioning System existed. An example of which is called the missionaries and cannibals problem, where you have 3 missionaries and 3 cannibals that need to cross the river, but the boat only holds 2 people. How do you write a program that gets the 3 missionaries and the 3 cannibals across together when only 2 can go at a time? And if you have a greater number of missionaries than cannibals on either shore or in the boat, well, you can guess what might happen. So that's a symbolic program that solves that problem. To the computer, the meaning of the symbols derives from the ways in which they can be combined, related to one another, and the arguments will include the number of missionaries or the number of cannibals that will be put in a boat at a time, and it will work through the problem and give you the answer. And there is a way to solve the problem that way. Sub-symbolic AI involved perceptrons. So this approach took inspiration from neuroscience and sought to capture the sometimes unconscious thought processes, what some have called fast perception, such as recognizing faces or identifying spoken words. Sub-symbolic AI programs do not contain anything that's readable. You could not tell how many missionaries or cannibals there were. It would just dump out the answer at the end. Early examples of these included the perceptron, which was invented in the late 50s by Frank Rosenblatt. The perceptron was an important milestone in AI and was the influential great-grandparent of modern AI's most successful tool, deep neural networks. So it was inspired by the way in which neurons process information. A neuron in the brain basically sums up all of the inputs it receives, and if it reaches a certain threshold point, the neuron fires, and that passes on something to the next neuron. And eventually it could cause a limb to move, it could cause you to blink, it could cause you to laugh, whatever it is that happens at the end. To a computer scientist, information processing in neurons can be simulated by a computer program, or perceptron, that has multiple inputs and one output. So it's a simple program that makes a yes or no decision based on whether the sum of the inputs meets some threshold value. And gives a good example here. You might get input from several friends on how much they liked a particular movie, but you trust some of those friends' taste in movies more than others. If the total amount of friend enthusiasm, giving more weight to your trusted friends, is high enough, then you decide to go to the movie. So that's kind of how perceptrons work. And they've used these to program the zip code identification system that was done with perceptrons, and it was very successful at doing that. Perhaps the most important term in computer science is algorithm, which refers to a recipe of steps a computer uses to solve a problem. Frank Rosenblatt's primary contribution to AI was his design of a specific algorithm called the perceptron learning algorithm that showed how a perceptron could be trained from examples to determine the weights and thresholds that would produce correct answers. So you could have 10 outputs and many, many inputs, the inputs being the dots of a dot matrix array around the digits to be encoded. So you're trying to detect the numbers 0 through 9. Think of an old dot matrix printer. The dot would either have an ink mark there or it would have no ink mark. It'd be white or it would be black. And if you scanned those arrays and said there's white or there's black, and those were all of the inputs, then you could have outputs that corresponded to 0 through 9. And the learning algorithm, showing it many, many 8s, many, many 7s, many, many 6s, was very good at training the algorithm to be able to read zip codes. So he showed that networks of perceptrons could learn to perform relatively simple perceptual tasks. Although they didn't know how well perceptrons would perform on more general AI tasks, this certainly didn't stop them from talking about this in very optimistic terms. July 1958, the New York Times featured this story. The Navy revealed the embryo of an electronic computer today that it expects will be able to walk, talk, see, write, reproduce itself, and be conscious of its existence. So even at the beginning, AI suffered from a height problem. So some of the limitations of perceptrons. In 1969, so this is 10 years later, Minsky and his MIT colleague Seymour Papert published a book, Perceptrons, in which they gave a mathematical proof showing the types of problems a perceptron could solve perfectly were very limited, and that the perceptron learning algorithm would not do well in scaling up to tasks requiring large number of weights and thresholds. So Minsky and Papert pointed out that if a perceptron is augmented by adding a layer of simulated neurons, types of problems a device can solve is, in principle, much broader. Perceptron with such an added layer is called a multi-layer neural network. Such networks form the foundations of modern AI. So there was an AI winter because there were two different schools of thought. One of them was the symbolic direction. Many people were pursuing that, where you create a bunch of rules. And then there was the sub-symbolic, which was the one that essentially looked at dots and looked at everything as inputs to a neural network, and you couldn't see what was going on inside. And it turns out that the sub-symbolic is the one that certainly has taken off. Easy things are hard. This simple lesson was noted by John McCarthy 50 years after the Dartmouth conference. AI was harder than we thought. Marvin Minsky pointed out, in fact, AI research had uncovered a paradox. Easy things are hard. The original goals of AI, computers that could converse with us in natural language, describe what they saw through their camera eyes, learn new concepts after seeing only a few examples, are things young children can easily do. But surprisingly, these easy things have turned out to be harder for AI to achieve than diagnosing complex diseases, beating human champions at chess and Go, and solving complex algebraic problems. By the mid-'80s, expert systems, symbolic AI approaches that relied on humans to create rules that reflect expert knowledge of a particular domain, were increasingly revealing themselves to be brittle, that is, error-prone, and often unable to generalize or adapt when presented with new situations. Researchers were discovering how much the human experts writing the rules actually rely on subconscious knowledge, what you might call common sense, in order to act intelligently. This kind of common sense could not easily be captured in programmed rules or logical deduction, and the lack of it severely limited any broad application of symbolic AI methods. There was a program called Mycin, which was an expert system. It was given about 600 rules that it used to help physicians diagnose and treat blood diseases. Programmers developing these rules spoke with many expert physicians about patient symptoms and medical test results, and it was actually pretty effective. It was a good example of symbolic AI. In contrast, as we've seen, sub-symbolic systems tended to be harder to interpret. No one knows how to directly program complex human knowledge or logic into these systems. They seem much better suited to perceptual or motor tasks for which humans can't easily identify rules. You can't easily write down rules for identifying handwritten digits, catching a baseball, or recognizing your mother's voice. We do these things automatically without conscious thought. As philosopher Andy Clark put it, the nature of sub-symbolic systems is to be bad at logic, good at Frisbee. So while there have been some attempts to construct hybrid systems that integrate sub-symbolic and symbolic methods, none of them have led to any striking success. The ascent of machine learning. AI began to get noticed. In 1997, IBM's Deep Blue chess playing system defeated the world chess champion Garry Kasparov. And by the mid-2000s, a more pervasive succession of AI accomplishments started sneaking up on us and proliferating at a dizzying pace. Google launched its automated language translation service, Google Translate. Google's self-driving cars showed up on the roads of Northern California. Virtual assistants such as Siri and Amazon Alexa were installed on our phones and in our homes. YouTube started providing impressively accurate automated subtitles for videos, and Skype offered simultaneous translation between languages and video calls. Facebook could recognize your face. IBM Watson program in 2011 defeated human champions on Jeopardy! 5 years later, millions of internet viewers were introduced to the complex game of Go, a longtime grand challenge for AI, when a program called AlphaGo stunningly defeated one of the world's best players in 4 out of 5 games. This period has been spoken of as the AI spring, and like every AI spring before it, our current one features experts predicting that general AI that equals or surpasses humans in most ways, will be here soon. There are a lot of predictions about this. While much of the optimism is based on the recent successes of deep learning, these programs, like all instances of AI to date, are still examples of what is called narrow or weak AI. These aren't as derogatory as they sound. They simply refer to a system that can perform only one narrowly defined task or small set of related tasks. AlphaGo is possibly the best Go player in the world, but it can't do anything else. It can't play checkers, tic-tac-toe, or Candyland. Google Translate can render an English movie review into Chinese, but it can't tell you if the reviewer liked the movie or not, and it certainly can't watch and review the movie by itself. So the terms narrow and weak are used to contrast with strong, human-level, general, or full-blown AI, sometimes called artificial general intelligence, AGI. That's the AI that we see in the movies that can do almost anything we humans can do, possibly more. General AI might have been the original goal of the field, but achieving it has turned out to be much harder than expected. Over time, efforts in AI have become focused on particular well-defined tasks, speech recognition, chess playing, autonomous driving, and so on. Recent appraisal of the field stated this well: pile of narrow intelligences will never add up to a general intelligence. General intelligence isn't about the number of abilities, but about the integration between those abilities. Not surprisingly, in the AI research community, there is considerable controversy over what human-level AI would entail. How can we know if we have succeeded in building such a thinking machine? Would such a system be required to have consciousness or self-awareness in the way humans do? Would it need to understand things in the same way a human does? Given that we're talking about a machine here, would we be more correct to say it is simulating thought, or could we say it is truly thinking? Timothy, could machines think? Alan Turing, the British mathematician who in the 1930s sketched out the first framework for programmable computers, published a paper in 1950 asking what we might mean when we ask, can machines think? The essence of this is saying the following: only when a machine feels things and is aware of its own actions and feelings, in short, is conscious, could we consider it actually thinking. And no machine could ever do this, ergo, no machine could ever actually think. The Turing test suggested the following: can machines think? Turing proposed an operational method to give it meaning. In his imitation game, now called the Turing test, there are two contestants, a computer and a human. Each is judged separately by a human who tries to determine which is which. The judge is physically separated from the two contestants, so cannot rely on visual auditory cues. Only typed text is communicated. Turing guessed that it would be 50 years before somebody was able to program computers to make them play the imitation game so well that an average interrogator would not have more than a 70% chance of making the right identification. In other words, 5-minute session, the average judge will be fooled 30% of the time. Turned out to be pretty accurate. Several Turing tests have been staged over the years. In 2014, the Royal Society in London was host to a Turing test demonstration. 5 computer programs, 30 human contestants, and in fact, chatbot named Eugene Guzman, created by a group of Russian and Ukrainian programmers, won the competition by fooling 10 or 33.3% of the judges. For who, what, when, where, and why. Melanie keeps referring to the concept that easy things are hard, especially in vision. She shows a picture in the book of a female soldier in a carpeted area. It could be in an airport. She's got a backpack on, petting a dog, and there's a balloon that says "Welcome Home" on it. And ask the question, what do you see in the photo? And there are many attributes that you will apply to this picture when you look at it. Is she just returning? Welcome home? Probably. What would an artificial intelligence program see when it looks at this? It might pick out that there's a balloon in it, that there's a woman in it, there's a backpack, a dog, but it wouldn't have any ideas about what was going on in the picture. And that's kind of her point, that humans have the ability to apply attributes to that. And that's something that's very hard for machines, in addition to singling out what the objects are in the image. The dog has a rope leash on. Does it know that rope is a leash attached to the dog? Things like that. So she talks about how researchers have been trying since the 50s to get computers to make sense of visual data. In 1966, Marvin Minsky and Seymour Papert, symbolic AI promoting MIT professors that she talked about earlier, proposed this summer vision project, which we talked about. And they didn't get very far in trying to do that. At a later point, people decided that they were going to put neural networks together and make them deep neural networks by having hidden layers in them. One of the big advances for object recognition was David Hubel and Torsten Wiesel, who were awarded a Nobel Prize for their discoveries of hierarchical organization in the visual system of cats and primates. They were inspired by a Japanese engineer, Kuniko Fukushima, who in the 70s developed one of the earliest deep neural networks dubbed the cognitron and its successor, the neocognitron. This neocognitron was an important inspiration for later approaches to deep neural networks, including today's most influential and widely used approach, convolutional neural networks, or as people in the field call them, convonets. Convonets are the driving force behind today's deep learning revolution in computer vision and other areas as well. They were first proposed in the 80s by the French computer scientist Yann LeCun, who had been inspired by Fukushima's neocognitron. So she's describing a little bit about how object recognition works in the brain and how convonets have allowed us to have machines be able to identify the typical objects that are in a picture: a bicycle, some flowers, a cat, a dog, etc. When your eyes focus on a scene, light falling on the eyes activates the cells in the retina. There's a grid of neurons in the back of the eye. These communicate their activation through the optic nerves into the brain, eventually activating neurons in the visual cortex, which resides in the back of the head. Visual cortex is organized as a hierarchy of layers of neurons like stacked layers of a wedding cake, where the neurons in each layer communicate their activations to neurons in the succeeding layer. So Hubel and Wiesel found evidence that neurons in the different layers act as detectors that respond to increasingly complex features appearing in the visual scene. If you think about this, one of the sets of neurons will respond to vertical edges, one to horizontal edges, one to dark, one to light. So as it goes from layer to layer, it is further defining what it is that you're looking at in the neural layers in the visual cortex, which is kind of interesting. That was mimicked with the deep neural network, where the convolutional neural networks, the different layers, are doing classification of the different characteristics in the image, and that's what helps this to become so accurate. So the input to the ConvNet is an image, array of numbers and stuff corresponding to the brightness and color of the image pixels. The final output is somewhere between 0 and 100% for each category of dog and cat, for example. In terms of what's going on between the input and the output, she describes these as activation maps. So imagine flying at night in an airplane over Los Angeles taking a photo. The lights seen in your photo form a rough map of the features in the lit up city. Imagine that you have a special camera that could produce separate photos for house lights, building lights, car lights. This is something like what the visual cortex does. Each important visual feature has its own separate neural map. The combination of these maps is what gives rise to our perception of a scene. A ConvNet, like the brain, represents the visual scene as a collection of maps reflecting the specific interests of a set of detectors. In one of her examples, these interests are different edge orientations. However, in ConvNets, the network itself learns what its interests are, or what its interests should be, and these depend on the specific task it's trained for. The maps are hierarchical, so the input to the units at layer 2 come out of the activations from layer 1, to layer 3 from layer 2. So from 2 to 3 to 4 to 5, there's a hierarchy there. So given an input image, each layer successfully performs its calculations, and finally layer 4, the network produces a set of activation maps for relatively complex features. These might include, so we're going to take a picture of some scene with animals in it, dogs or cats. The different activation maps might include eyes, leg shapes, tail shapes, or anything else that the network has learned is useful for classifying the objects of interest that it's trained on. In this case, it's dogs and cats. At this point, it's time for the classification module to use these features to predict which object is in the picture. So, as a summary of Hubel and Wiesel's findings on the visual brain cortex A, ConvNet takes an input image and transforms it via convolutions into a set of activation maps with increasingly complex features. Features at the highest convolutional layer are fed into a traditional neural network, which is called the classification module, and that outputs confidence percentages for the known object categories. The category with the highest confidence is returned as the classification of the image. So you could have 4 outputs for dogs and cats and rabbits and squirrels, and each of the piles of pictures, if you will, that they're trained on that says this is a rabbit, this is a squirrel, will create a more likely output in the category of squirrel or rabbit or dog or whatever it is. ConvNets and ImageNet. So Jan LeCun, the inventor of ConvNets, worked on neural networks all his life. He and Geoffrey Hinton, other neural network loyalists, believe that improved, larger versions of ConvNets and other deep networks would conquer computer vision if only they could be trained with enough data. There was a competition called the Pascal, P-A-S-C-A-L, Visual Object Classes Competition, and it ran from 2005 to 2010 was the most prominent one, and then by 2010 it featured about 15,000 photographs. You download them from Flickr, and with human-created labels for 20 object categories: person, dog, horse, sheep, car, bicycle, sofa, etc. Potted plants were the hardest ones to do. And they had these competitions, but they didn't have enough data to train these until Fei-Fei Li, young computer vision professor at Princeton, was particularly focused on this goal. She learned of a project by a fellow Princeton professor, George Miller, he was a psychologist, to create a database of English words arranged in hierarchy, moving from most specific to most general, with groupings among synonyms. For example, consider the word cappuccino. The database called WordNet contains the following information about this term, where an arrow means is a kind of. Cappuccino, arrow coffee, arrow beverage, arrow food, arrow substance, arrow physical entity, arrow entity. So this database was created with all of these links together to associate words with each other, which could be used in natural language processing systems. But Fei-Fei Li had a new idea, create an image database that's structured according to the nouns in WordNet, where each noun is linked to a large number of images containing that noun. Everybody said that we need to have more images and we need to have more labeled images so that we can teach our systems what's in the image. So the group was at an impasse. The work was very slow and taxing. They couldn't get enough students to work on this until Fei-Fei Li stumbled upon a 3-year-old website that could deliver the human smarts that ImageNet needed. The website had the strange name, Amazon Mechanical Turk. The Mechanical Turk is a marketplace for work that requires human intelligence. The service connects requesters, people who need a task accomplished that's hard for computers, with human workers who are willing to lend their human intelligence to a requester's task for a small fee. For example, labeling objects in a photo, 10 cents per photo. Hundreds of thousands of workers have signed up from all over the world. Mechanical Turk is the embodiment of Marvin Minsky's easy thing or hard dictum, that human workers are hired to perform the easy tasks that are currently too hard for computers. The Mechanical Turk name came from a famous 18th century AI hoax. The original Mechanical Turk was a chess-playing intelligent machine which secretly hid a human who controlled a puppet, the Turk, dressed like an Ottoman sultan, that made the moves. Evidently, it fooled many prominent people at the time, including Napoleon Bonaparte. Amazon's service, while not meaning to fool anyone, is like the original Mechanical Turk. So she realized that if a group paid tens of thousands of workers on Mechanical Turk to sort out the irrelevant images for each of the WordNet terms, the whole data set could be completed within a few years at a relatively low cost. In a mere 2 years, more than 3 million images were labeled with corresponding WordNet nouns to form the ImageNet data set. For this project, Mechanical Turk was a godsend. As one might expect, ImageNet competitions started to pop up. These were certainly more challenging than the Pascal ones. 35 different programs were competing in the very first one. There were 1.2 million labeled training images provided to the teams. There were 1,000 possible categories instead of Pascal's 20, and they were a subset of WordNet terms chosen by the organizers. Categories are random-looking assembly of nouns ranging from familiar and commonplace, lemon, castle, grand piano, somewhat less common, viaduct, hermit crab, metronome, down to the downright obscure Scottish deerhound, Rudy Turnstone, hussar monkey. Hussar monkey? I don't know. Some of the photographs have only one object. Others contain many objects, including the correct one. So because of this ambiguity, a program gets to guess 5 categories for each image. The highest scoring program in 2010 was a support vector machine, which is a predominant object recognition algorithm of the day. It employed sophisticated math to learn how to assign a category to each input image. Using the top 5 accuracy metric, this winning program was correct on 72% of the 150,000 test images. Notably, there were no neural networks among the top scoring program. The following year, the highest scoring program, also using support vector machines, showed a respectable but modest improvement, getting 74% of the test images correct. However, these were upended in 2012. ImageNet competition, the winning entry achieved 85%. So that's 74 to 85%. That's quite a jump. It was a shocking development. The winning entry did not use support vector machines or any of the other dominant computer vision methods of the day. Instead, it was a convolutional neural network. This particular convonet has become known as AlexNet, named after Alex Krizhevsky, its main creator, who was then a graduate student at the University of Toronto. He was supervised by eminent neural network researcher Geoffrey Hinton. His success with AlexNet sent a jolt through the computer vision and broader AI communities, suddenly waking people up to the power of convonets, which most AI researchers hadn't considered a serious contender in modern computer vision. At the same time, Geoffrey Hinton's group was also demonstrating that deep neural networks trained on huge amounts of labeled data were significantly better than the current state of the art in speech recognition. Within a year, a small company started by Hinton was acquired by Google, and Hinton and his students, Krzyzewski and Sutskever, became Google employees. This acqui-hire instantly put Google at the forefront of deep learning. Soon after, Jan LeCun was lured away from his full-time New York University professorship by Facebook to head up its newly formed AI lab. What was it that enabled ConvaNets, which seemed to be dead at the end of the 90s, to suddenly dominate the ImageNet competition and subsequently most of computer vision in the last half a decade? Turns out that the recent success of deep learning is due less to new breakthroughs in AI than to the availability of huge amounts of data, thank you, Internet, and very fast parallel computing hardware. These factors, along with improvements in training methods, allow 100-plus layer networks to be trained on millions of images in just a few days. Jan LeCun himself was taken by surprise at how fast things turned around for his ConvaNets. It's rarely the case where a technology that's been around for 20 to 25 years, basically unchanged, turns out to be the best. The speed at which people have embraced it is nothing short of amazing. I've never seen anything like this before. ConvaNets have created a sort of ConvaNet gold rush. Using ConvaNets trained with deep learning, image search engines offered by Google, Microsoft, and others are able to vastly improve their Find Similar Images feature. Facebook labeled your uploaded photos with names of your friends and registered a patent on classifying the emotions behind facial expressions in uploaded pictures. Twitter developed a filter that could screen tweets for pornographic images, and several video sharing sites have applied tools to detect imagery associated with terrorist groups. ConvaNets can be applied to video and used in self-driving cars to track pedestrians or to read lips and classify body language. They can even diagnose breast cancer and skin cancer from medical images, determine the state of diabetic retinopathy, and assist physicians in treatment plans for prostate cancer. So have ConvaNets surpassed humans in object recognition? When you read about machines identifying objects correctly, say, given an image of a basketball, the machine would output basketball. But of course, on ImageNet, correct identification means only that the correct category is in the machine's top 5 categories. Given an image of a basketball, if the machine outputs croquet ball, bikini, warthog, basketball, and moving van, it's considered correct. But it's notable that the best top 1 accuracy, the fraction of test images on which the correct category comes up at the top of the list, was only about 82%. Compared with 98% of top 5 accuracy. As far as I know, nobody has reported the comparison between machines and humans on top 1 accuracy. And I would think if we were asking for it to find a particular thing, we would want to have it be similar to a human and hit the top 1 accuracy. Here's a caveat that might surprise you. When a human says a photo contains, say, a dog, we assume it's because the human actually saw a dog in the photo. But if a ConvaNet correctly says dog, how do we know it's actually basing this classification on a dog in the image? Maybe there's something else in the image, a tennis ball, a frisbee, a chewed-up shoe, that's associated with dogs in the training images. ConvaNet is recognizing these. These kinds of correlations have often ended up fooling machines. One of these was when people take pictures of dogs, oftentimes the things in the background are blurred, and it was starting to associate blurred backgrounds with dogs, even if a dog wasn't in it. Melanie closes out this chapter saying she's focused on object recognition because this has been the area which computer vision has recently seen the most progress. However, it's obviously a lot more to vision than just recognizing objects. The goal of computer vision is to get the machine to describe what it sees. The machines will need to recognize not only objects, but also their relationships to one another and how they interact with the world. When the objects in question are living beings, you have to know something about their actions, goals, emotions, likely next steps, all the other aspects that figure into telling the story of a visual scene. As the computer vision expert Ali Farhadi told the New York Times recently, we're still very, very far from visual intelligence, understanding scenes and actions the way humans do. Why are we so far? It seems that visual intelligence is not easily separable from the rest of intelligence, especially general knowledge, abstraction, and language, abilities that interestingly involve parts of the brain that have many feedback connections to the visual cortex. Additionally, it could be that the knowledge needed for human-like visual intelligence, for example, making sense of that soldier and dog photo from the beginning of the previous chapter, can't be learned from millions of pictures downloaded from the web, but has to be experienced in some way in the real world. In the next chapters, I'll look more closely at machine learning and vision, focusing in particular on the differences between the ways humans and machines learn and trying to tease out just what the machines we have trained have actually learned. A closer look at machines that learn. In this chapter, Melanie looks in more detail at how machines, particularly convo nets, learn and how their learning processes contrast with those of humans. I'll also explore how differences between learning in convo nets and in humans affect the robustness and trustworthiness of what's learned. The learning from data approach of deep neural networks has generally proved to be more successful than the good old-fashioned AI strategy, which was called GOFI, in which human programmers construct explicit rules for intelligent behavior. The most successful convo nets learn via a supervised learning procedure, gradually changing their weights as they process the examples in the training set again and again over many epochs, which are passes through the training set, learning to classify each input as one of a fixed set of possible output categories, like we spoke about before. Be a pile of pictures that are cats and dogs, squirrels and rabbits. A convo net will keep adjusting itself. When it gets it wrong, it'll go back, adjust the weights, and try it again, run through the whole stack again. In contrast, even the youngest children learn an open-ended set of categories and can recognize instances of most categories after seeing only a few examples. Moreover, children don't learn passively. They ask questions. They demand information on the things they're curious about. They infer abstractions of and connections between concepts. And above all, they actively explore the world. It's inaccurate to say that today's successful convo nets learn on their own. As we saw in the previous chapter, in order for a convo net to learn to perform a task, a huge amount of human effort is required to collect, curate, label the data, as well as to design the many aspects of the convo net's architecture. There are many values to set, complex design decisions to make, and these settings and designs interact with one another in complex ways to affect the ultimate performance of the network. Tuning the hyperparameters might sound like a pretty mundane activity, but doing it well is crucial to the success of these convo nets. As Eric Horowitz, director of Microsoft's research lab, characterized it, right now, what we are doing is not a science, but a kind of alchemy. People who can do this kind of network whispering form a small exclusive club. It's almost like an art form to get the best out of these systems. There's only a few hundred people in the world that can do it really well. Big data is the secret to all of this. Deep learning requires big data. The big data was required for them to be able to successfully train convo nets to be able to identify what's in an image, and then to tune those systems so that they worked as well as they do today. So where does all this data come from? It comes from us. Have you ever put a photo of a friend on your Facebook page and commented on it? Facebook thanks you. That image and text might have been used to train its face recognition system. Have you ever identified a picture in order to prove to a website that you're not a robot? Your identification might have helped Google tag an image for use in its training in image search systems. So we've all been part of the training regime for these AI systems. Tesla owners, of course, aren't required to label all the objects on the videos, but somebody has to. In 2017, the Financial Times reported that most companies working on this technology employ hundreds or even thousands of people, often in offshore outsourcing centers in India or China, whose job it is to teach the robocars to recognize pedestrians, cyclists, other objects. Workers do this by manually marking up or labeling thousands of hours of video footage, often frame by frame. The supervised learning approach, using large data sets and armies of humans, works well for at least some of the visual abilities needed for self-driving cars. But what about in the rest of life? Virtually everyone working in the AI field agrees that supervised learning is not a viable path to general-purpose AI. As the renowned AI researcher Andrew Ng has warned, requiring so much data is a major limitation of deep learning today. The issue is compounded by the so-called long-tail problem. The vast range of possible unexpected situations an AI system could be faced with. Very common situations, such as encountering a red traffic light or a stop sign, are rated as having high likelihood. Medium likelihood situations include broken glass, wind-whipped plastic bags, Not encountered every day, depending on where you live, but not uncommon. Less likely that your self-driving car would encounter a flooded road or lane markings obscured by snow, and even less likely that you would face a snowman in the middle of a high-speed road. So the term long tail comes from statistics in which certain probability distributions are shaped like the upside-down U, and the long tail is at the very left and right. Most real-world domains for AI exhibit this kind of long tail phenomenon. So here are two real-world examples. March 2016, there was a massive snowstorm forecast in the northeast of the U.S., and reports appeared on Twitter that Tesla vehicles' autopilot mode, which enables a limited auto driving mode, were getting confused between the lane markings and the salt lines laid out on the highway in anticipation of the storm. They're like salt tracers. They look like solid lane markings in the middle of the lane. They dropped from a salt distribution truck in a liquid form. In February 2016, one of Google's prototype self-driving cars, while making a right turn, had to veer to the left to avoid sandbags on the right side of a California road. The car's left front struck a public bus driving in the left lane. Each vehicle had expected the other to yield. Perhaps the bus driver expected a human driver who would be more intimidated by the much larger bus, but that wasn't the case, and there was an accident. Humans make mistakes all the time in driving. Any one of us might have hit that bus, but had we been veering around the sandbags, we have a fundamental competence, vast background of the world, knowing that bus is going to be really big and it's not going to move, and we probably would have hit the sandbag instead. The question of what is the network learning? One of the graduate students in Melanie's research group was doing some classification of photographs into one of two categories: contains an animal, does not contain an animal. The program performed very well in this task, but what did it actually learn? Well, it learned to classify images with a blurry background as contains an animal, whether or not the image actually had an animal. And that's because the photos in the training sets, when an animal was jumping or moving or whatever, the background tended to be blurred. So it hadn't learned to recognize animals. Instead, it used simpler cues, such as the blurry background, that were statistically associated with animals. So this is a common phenomenon seen in machine learning, where it learns what it observes in the data rather than what you, the human, might observe. His network, Will's network, overfitted to its specific training set, thus can't do a good job of applying what it learned to images that differ from those it was trained on. One group showed that if convo nets are trained on images downloaded from the web, like those in ImageNet, they perform poorly on images that were taken by a robot moving around a house with a camera. It seems that random views of household objects can look very different from the photos people get from the web. Others have shown that superficial changes to images, such as slightly blurring or speckling an image, changing some colors, or rotating the objects in the scene, can cause convo nets to make significant errors even when those perturbations don't affect humans' recognition of the object. This unexpected fragility of convo nets, even those who might have been said to surpass humans at object recognition, indicates that they are overfitting to their training data and learning something different from what we are trying to teach them. The unreliability of convo nets can result in embarrassing, potentially damaging errors. Google suffered a public relations nightmare in 2015 after it rolled out its automated photo tagging feature using a ConvoNet in its Photos app. In addition to correctly tagging images with generic descriptions such as airplanes, cars, and graduation, the neural network tagged a selfie featuring two African Americans as gorillas, as shown in the picture in the book. Commercial face recognition systems tend to be more accurate on white male faces than on female or non-white faces. Researcher at Microsoft and an activist for fairness and transparency in AI pointed out that one widely used data set for training face recognition systems contains faces that are 77.5% male and 83.5% white. Not surprising, because the images are skewed toward featuring famous or powerful people who are predominantly white and male. Face recognition systems are increasingly being deployed as a secure way to identify people in credit card transactions, airport screening, security cameras, and it may only be a matter of time before they're used to verify identity in voting systems, among other applications. Even small differences in accuracy between racial groups can have damaging repercussions in civil rights and access to vital services. One research group noted that their AI system, trained on a large data set of photos of people in different situations, would sometimes mistakenly classify a man as a woman when the man was standing in a kitchen, an environment in which the data set had more examples of women, then AI systems cannot typically show their work. Of course, we all remember a teacher saying, show your work so you can show how you came up with your answer. Most deep networks have no ability to show their work. We can't look under the hood and see how humans have come up with their answers either. In many cases, humans can't always explain their thought processes either, and you generally can't look under the hood into other people's brains or into their gut feelings to figure out how they came to any particular decision. But humans tend to trust that other humans have correctly mastered basic cognitive tasks such as object recognition and language comprehension. In part, you trust other people because you believe their thinking is like your own. You assume most often that other humans you encounter have sufficiently similar life experiences to your own, and thus assume they are using the same basic background knowledge, beliefs, and values that you do in perceiving, describing, and making decisions about the world. In short, where other people are concerned, you have what psychologists call a theory of mind, a model of the other person's knowledge and goals in particular situations. None of us have a similar theory of mind for AI systems, such as deep networks, which makes it harder to trust them. It shouldn't come as a surprise that one of the hottest new areas of AI is called explainable AI, transparent AI, or interpretable machine learning. These terms refer to research on getting AI systems, particularly deep networks, to explain their decisions in a way that humans can understand. Fooling deep neural networks. There's another dimension to the AI trustworthiness question. Researchers have discovered that it's surprisingly easy for humans to trick deep neural networks into making errors. If you want to deliberately fool such a system, there turns out to be an alarming number of ways to do so. Remember AlexNet, which we discussed earlier, the convolutional neural network that won the 2012 ImageNet challenge and set in motion the dominance of convo-nets in much of today's AI world. However, a research paper authored by Christian Szegedy of Google and several others with deceptively mild title, Intriguing Properties of Neural Networks. One of the intriguing properties described in the paper was that AlexNet could be easily fooled. In fact, they discovered that you could take an ImageNet photo that AlexNet had classified correctly with high confidence, for example, school bus, and distort it by making very small changes to its pixels. So the distorted image looked completely unchanged to humans, but was now classified with very high confidence by AlexNet as something completely different, such as ostrich, or if they turned it on its side, it thought it was a snowplow. Szegedy and his collaborators created a computer program that could, given any photo from ImageNet that was correctly classified by AlexNet, could find specific changes to the photo to create a new adversarial example that looked unchanged to humans but caused AlexNet to give highest confidence to an incorrect category. They also found that the susceptibility to adversarial examples wasn't special to AlexNet. They showed several other convolutional neural networks with different architectures, hyperparameters, and training sets had similar vulnerabilities. Not long after this paper appeared, a group from the University of Wyoming published an article with a more direct title, Deep neural networks are easily fooled. By using a biologically inspired computational method called genetic algorithm, the Wyoming group was able to computationally evolve images that looked like random noise to humans, but for which AlexNet and other convolutional neural networks assigned specific object categories with greater than 99% confidence. The Wyoming group noted that deep neural networks, DNNs, see these objects as near-perfect examples of recognizable images. Of course, if humans looking at this couldn't see anything at all in them, they just look like noise. Even if you squint your eyes, you don't really pick up anything but a few edges out of the images, and they're in the book. Indeed, these two papers and subsequent related discoveries raised not only questions, but also genuine alarm in the deep learning community. If deep learning systems so successful at computer vision and other tasks can easily be fooled by manipulations that humans can't even detect, how do we say these networks learn like humans or equal or surpass humans in their abilities? This has re-energized the small research community focusing on adversarial learning, that is, developing strategies that defend against potential human adversaries who could attack machine learning systems. Other groups developed small inconspicuous stickers that could be placed on a traffic sign, resulting in a ConvoNet-based vision system similar to those used in self-driving cars, to misclassify the sign. For example, a stop sign is classified as a speed limit sign. Another group showed that it's not hard to alter an X-ray or microscopy image in a way that's imperceptible to humans, but causes the network to change its classification from, say, 99% confidence that the image shows no cancer to 99% confidence that cancer is present. These types of attacks could potentially be used by hospital personnel to create fraudulent diagnosis in order to charge insurance companies for additional lucrative diagnostics tests. To my mind, the ultimate system is one of understanding. Consider where AlexNet mistakes a school bus for an ostrich or a snowplow. Why would this be very unlikely to happen in a human? We humans understand many things about the objects we see that are unknown to AlexNet or any other AI systems. We know what they look like in 3 dimensions. We can imagine this from a 2-dimensional photo. We know what functions the object has, the role that the objects play in its overall function, and what context an object usually appears. Seeing it brings up memories of other objects and other circumstances. All of this background feeds into the human ability to robustly recognize a given object. Even the most successful AI vision systems lack this kind of understanding and the robustness that it confers. Jeff Clune, an AI researcher at the University of Wyoming, made a very provocative analogy when he noted, there's a lot of interest in whether deep learning is real intelligence or a clever Hans. Clever Hans was a horse in the early 20th century Germany who could, his owner claimed, perform arithmetic calculations as well as understand German. The horse responded to questions such as, what is 15 divided by 3? By tapping his hoof the correct number of times. The clever Hans became an international celebrity, and a careful investigation eventually revealed that the horse didn't actually understand the questions or mathematical concepts, but was tapping in response to subtle unconscious cues given by the questioner. Clever Hans has become a metaphor for any individual or program that gives the appearance of understanding but is actually responding to unintentional cues given by a trainer. Does deep learning exhibit true understanding, or is it instead a computational clever Hans responding to superficial cues in the data? This is currently the subject of heated debates in the AI community, compounded by the fact that AI researchers don't necessarily agree on what true understanding is. Recognition of the success of these networks has to be tempered with a realization that they can fail in unexpected ways because of overfitting to their training data, long-tail effects, and vulnerability to hacking. Moreover, the reasons for decisions made by deep neural networks are often hard to understand, which makes the failures hard to predict or fix. Researchers are actively working on making deep neural networks more reliable and transparent, but the question remains, will the fact that these systems lack human-like understanding inevitably render them fragile, unreliable, and vulnerable to attacks? And how should this factor into our decisions about applying AI systems in the real world? The next chapter explores some of the formidable challenges of balancing the benefits of AI with the risks of its unreliability and misuse. So I hope you join us next time for part 2 of Melanie Mitchell's book, Artificial Intelligence, A Guide for Thinking Humans. Thank you. That's a wrap.